Okay guys, let's begin our discussion over the CBSE pattern question exercises for the chapter Determinants. The first question carrying 1 mark says that in the open interval pi by 2 to pi, find the value of x for which this particular given 2 cross 2 matrix is singular. Matrix is singular means if I am saying A is this given matrix which is 2 sin x, 3, 1, 2 sin x. If A is this, A is singular, if it is given that A is singular, this means that its determinant is equal to 0. That's what is a singular matrix, which implies determinant of 2 sin x, 3, 1, 2 sin x. This determinant is 0. This means what? Product of the diagonals minus product of off diagonals. So this gives you 4 sin square x minus 3 into 1 is 3 equals 0, which implies 4 sin square x equals 3, which implies sin square x equals 3 by 4. Now from here, if you try to compute sin x, you are going to get plus minus root 3 by 2. But actually I am avoiding the minus sign. Why? Because x is given to be lying in pi by 2 to pi open interval, and in our very quadrant system, if you remember, if I talk about the quadrant system, first quadrant x is lying between 0 to pi by 2, second pi by 2 to pi, right, third pi to 3 pi by 2, 3 pi by 2 to 2 pi. So if my x is lying between pi by 2 and pi, by the very sign convention, I know from ASTC rule that sine and cosec are positive in the second quadrant. This is the second quadrant, this is the third quadrant, this is the fourth quadrant, this is the first quadrant. In the second quadrant, if x is lying between pi by 2 to pi, sine ratio of these x's are going to be positive values. So sin x, if x is coming from the second quadrant, cannot be negative, it has to be positive. So sin x has to be root 3 by 2. Now sine of which angle lying in the second quadrant is root 3 by 2? Right now, by a table, by a very table that we learned for sine and cosine ratios in our 10th standard, we all know that sine ratio of 60 degrees is root 3 by 2. That means sine of pi by 3 is root 3 by 2. But pi by 3 does not lie in the second quadrant. It actually lies in the first quadrant. I want an angle in the second quadrant at which the value of sine is root 3 by 2. We all know that sine x is same as sine of pi minus x, right? Sine theta is same as sine of pi minus theta, and pi minus theta lies in the second quadrant. That means sine pi by 3 is same as sine of pi minus pi by 3, which is sine of 2 pi by 3, which is root 3 by 2. So in the first quadrant, if you want the angle, it is pi by 3 at which sine ratio is root 3 by 2. In the second quadrant, the angle that you want is 2 pi by 3 at which the sine ratio is root 3 by 2. I want x's value to be lying in second quadrant, so that means x's value should be 2 pi by 3 for sine ratio of it to be root 3 by 2. So this implies x is equal to 2 pi by 3 lying in the second quadrant. So what is the value of x lying in the second quadrant for which this matrix is singular? X's value should be 2 pi by 3, so that this matrix comes out to be a singular matrix. Moving ahead, what is it that we have? Let A be a square matrix of order 3 cross 3. Write the value of determinant of 2A if determinant of A is 4. Now this requires a very, very small basic concept related to determinant of a square matrix of order n. You know that if A is a square matrix of order n, then determinant of k times A is k to the power n times determinant of A. By using this particular property of square matrices and determinants, I am actually given that determinant of A is 4. Determinant of 2A will be what? A is a square matrix of order 3 cross 3. So 2 to the power 3 determinant of A, which means 8 into 4, that is 32. So 32 is the value of determinant of 2A if determinant of A is 4 and A is a square matrix of order 3 cross 3. Easy enough, only usage of this particular concept. Next I have write the value of this particular determinant. Okay, so there is this determinant given to you of order 3 cross 3. It's pretty easy. Clearly you can see this is A minus B minus C, C minus A, B minus C minus A minus B, C minus A minus B minus C. So if I say that let del be the representative of the value of this determinant, A minus B minus C, C minus A, B minus C minus A minus B, C minus A minus B minus A. In this situation, if I carry out the operation, rho 1 goes to rho 1 plus rho 2 plus rho 3, then the value of this determinant is not going to change. A minus B plus B minus C plus C minus A. A minus B plus B minus C plus C minus A. This also. B minus C plus C minus A plus A minus B. And this one will be C minus A plus A minus B plus B minus C. Rest everything same. B minus C, C minus A minus B, C minus A minus B, B minus A. This is B minus C. Now you can see plus A minus A plus C minus C plus B minus B, plus B minus B plus A minus A plus C minus C, plus C minus C plus B minus B plus A minus A. You can see there is a 0 over here, 0 over here, 0 over here. Any determinant with any one row completely full of zeros is actually equal to 0, and therefore the value of this determinant is nothing but simple 0. Next question we have, if for any 2 cross 2 square matrix, A into adjoint of A is this 2 cross 2 matrix, then write the value of determinant of A. Now for this, you need to know one concept, that A is a square matrix of order n cross n, then clearly adjoint of A is also a square matrix of order n cross n. Determinant of adjoint of A is same as determinant of A to the power n minus 1. Okay, this is a relationship between determinant of A and determinant of adjoint of A. Using this relationship between determinant of A and determinant of adjoint of A, we will be tackling this question. Here we have A into adjoint of A is given to be this 2 cross 2 matrix 8, 0, 0, 8. If two matrices are same, the determinants are also same. This implies determinant of A into adjoint of A is equal to 8, 0, 0, 8, this determinant. What is this? 2 cross 2 determinant, product of diagonals minus product of off diagonals, 64 minus 0, that is 64. Now, determinant of A into B is determinant of A into determinant of B. This is one matrix, this is one matrix. This is determinant of A into determinant of adjoint of A. This is equal to 64. This is determinant of A. What is determinant of adjoint of A? A is a square matrix of order 2. Basically, if this is coming out to be 2 cross 2 matrix, clearly this is 2 cross 2, this is 2 cross 2, right? That is what is given to me. A is a square matrix of order 2 cross 2. So, adjoint of A is also a square matrix of order 2 cross 2. Their resultant product matrix is also of 2 cross 2. If A is a matrix of order 2 cross 2, determinant of adjoint of A will be determinant of A to the power 2 minus 1. So, this is determinant of A to the power 2 minus 1. Which means determinant of A square is 64, which implies determinant of A is plus minus 8. And that is how you compute the value of determinant of A. Moving ahead, we have find the equation of the line joining these 2 points using determinant approach and find the value of k if this point is a point such that the area of triangle ABD is 3 square units. This is pretty conceptual based question. Here they are saying that there is a point joining A1, 3 and B0, 0. So say I say this is A and this is B, this is 1, 3, this is 0, 0. First of all, in order to find the equation of this line joining A and B, I take a point P, x, y on this line. Varying point, obviously, because I need the equation of this line, so I need to see what is the property which is being followed by all the points lying on this line. So I take an arbitrary point on this line. Now if you see, if these are 3 collinear points, obviously the area of the triangle APB is 0. I am saying let P x, y be a point on AB. This implies area of triangle APB is 0, which implies determinant approach. What is the formula? 1, 3, 1 x, y 1 0, 0, 1. This is 0. This is the formula. Fine. 1, 3 is the vertex of first vertex, x, y second, 0, 0 third, 1 throughout on the third column, half multiplied by this determinant equals 0. Compute. If I compute it along this, I get 1 by 2. This is 1, y minus 0, minus 3, here it will be x minus 0, and then it will be plus 1, 0 minus 0. So this will be equal to half y minus 3x equals 0, which implies y equals 3x. Because this 2 will go over here, it will be 0, you will be left with y minus 3x equals 0, which means y equals 3x is the equation of the line joining A 1, 3 and B 0, 0. Because x and y are satisfying this relationship and x, y was an arbitrary point chosen on the segment. Therefore, this is the relationship being exercised by every point on the segment. So, this represents the equation of the given line. Now that we have got the equation, it is also saying find the value of k if dk, 0 is a point such that area of triangle ABD is 3 square units. So, the point given to you is k, 0, somewhere here suppose is D k, 0, join it with A, join it with B, area of this triangle, area is given to be 3 square units. Fine. If area is given to be 3 square units, we have already done the first part. Let's tackle the next part now. So now, area of triangle ABD is 3 square units. Area is always a non-negative quantity. That means mod of the area. Mod of the area ABD. So it is 1, 3, 1, 0, 0, 1, K, 0, 1. Mod of this particular area. This is equal to 3. If I remove the mod, what do I get? 1, 3, 1, 0, 0, 1, K, 0, 1. This is equal to plus minus 3 because I have removed the mod sign. Solve this determinant. If you solve it along, say, second row, you will be having 1, this cancelled out, so you are left with 0 minus 3k. So this is 2 is going to go that side, so I am not writing half. This gone, you are left with 0 minus 3k. So minus 3k equals plus minus 6. This implies k is equal to plus minus 2. Here one more minus is going to come because this will be 2 1th element, 2 2th and 2 3th element. So minus 1 to the power 2 plus 3, that is minus 1 to the power 5. So minus of this. So this will be 3k equals plus minus 6 or k equals plus minus 2. So it is for k equals plus minus 2 that the area of this triangle is equal to 3 square units. Understood? That's how you tackle this question, having two parts. One is the equation, other is the value of k. Going to the next question, we have using properties of determinant, prove that the value of this particular determinant is equal to 9y square times x plus y. Let's write the value as del of this determinant, and then we have to prove that this del is equal to 9y square into x plus y. So this is x plus y, x plus 2y, then you have x plus 2y, x plus y, and then you have x plus y, x plus 2y and x. According to the pattern, clearly if you apply rho 1 goes to rho 1 plus rho 2 plus rho 3, you get del is equal to x plus 2y plus x plus y. So it is 3x plus 3y, x plus y plus x plus 2y, again 3x plus 3y, x plus 2y plus x plus y plus x, again 3x plus 3y. Here you have x plus 2y, x plus y, then x plus y, x plus 2y, x. Clearly you can see in the first row all the three elements are same, so I will be taking out that common, taking 3x plus 3y common from the first row. You get del is equals to 3x plus 3y times 1 1 1 x plus 2y, x plus y, x plus y, x plus 2y, x. Clearly for simplification, in order to compute the value of this determinant, I want maximum number of zeros in any row or any column. So I will be taking column 2 goes to column 2 minus column 1, and column 3 also goes to column 3 minus column 1. This gives me del is equals to 3x plus 3y, column 1 as it is, column 2 minus column 1, 1 minus 1 0, x minus 2y. X minus 2y just gives you minus 2y. X plus 2y minus x minus y, 2y minus y is y. Then column 3 minus column 1, 1 minus 1 0 again, x plus y minus x minus 2y. So y minus 2y is minus y. Then x plus y minus x minus 2y. So y minus 2y is minus y. X minus y, this is again minus y. Clear? Now you expand along the first row. Expanding. So let me make this demarcation here. Expanding along first row, we get del is equals to 3x plus 3y multiplied by, so first row, expanding along the first row, you would be getting minus 2y into minus y, which is 2y square plus y square. This gives you 3 common x plus y into 3y square, which is 9y square into x plus y. So you have got the value of determinant to be equal to 9y square into x plus y. Clear? Pretty nice question. Next we have the 7th one. If fx is this, using properties of determinant, find the value of f of 2x minus f of x. Now this is a pretty important question. Let's try to compute the value of f of 2x minus f of x. The moment I write f of x as a determinant involving x, so you can start like we have fx is equal to a minus 1, 0, ax a minus 1, ax square ax a. clearly you can see in the first column there is A common. So taking A common from column 1, you have fx is equal to A common. Now you have 1x, x square minus 1a, ax 0 minus 1a. Now I am saying column 1 goes to column 1 plus column 2, so that 1 minus 1 gives me 0 over here and I get a simplified f of x. So a is outside, 1 plus minus 1 is 0, x plus a, I am adding column 1 and column 2, x square plus ax. Then it is minus 1a ax, 0 minus 1a. Okay, so here if I expand along the first row, a is already there, minus of minus 1 gives me 1, and I have x plus a into a plus 1 into x square plus ax. Fine, this gone, you have x plus a into a plus 1 into x square plus ax. So this gives me a. This is ax plus a square plus x square plus ax. So x square plus 2ax plus a square is x plus a whole square. X square plus a square plus 2ax. If f of x is coming out to be a times x plus a whole square, I want f of 2x minus f of x. F of 2x will be equal to a 2x plus a whole square. I have f of 2x with me, I have f of x with me. Let's compute f of 2x minus f of x. So f of 2x minus f of x, f of 2x is what? A 2x plus a whole square minus a x plus a whole square. So a is common, x plus a whole square. A square minus b square, a plus b into a minus b is what it is. So a square minus b square, a plus b into a minus b. Plus a minus a cancels out, you are left with 3x plus 3a, and here it is just an x. Fine. So you have ax or 3ax into x plus a. 3 common, 3 into a into x, whole multiplied by x plus a. So 3ax into x plus a is the value of f of 2x minus f of x. Moving to the next question, we have, if a is this, then find transpose of a's inverse. Okay, you have to find the inverse of a transpose. See, you all know that inverse of a matrix exists only when its determinant is not equal to 0. Until and unless determinant of A transpose is not equal to 0, I cannot talk about the existence of its inverse, and I know that the determinant of A transpose is same as determinant of A. So I will have to compute the determinant of A to ensure that the determinant of A transpose is not equal to 0. If A is this, what is determinant of A? It is determinant of 1, minus 2, 3, 0, minus 1, 4, minus 2, 2, 1. Expand along the first row, not a problem. You have 1, minus 8, that is minus 9, plus 2, you have 0 plus 8, then 3, you have 0 minus 2. So this is minus 9 plus 16 minus 6. So this gives me minus 9 plus 10, that is 1, which is not equal to 0. So clearly determinant of A is not equal to 0. Therefore, A is non-singular, which implies A inverse exists. But am I interested in the existence of A inverse? I am not interested in the existence of A inverse. I am interested in the existence of transpose of A's inverse. But we should know that transpose of or inverse of A transpose is actually nothing but transpose of A inverse. if I am able to compute the inverse of A matrix and take its transpose, the resultant matrix will be transpose of A's whole inverse. And it is ensured that because A is non-singular, A transpose is also non-singular because both of them have the same determinant. So even the determinant of A transpose is not equal to 0. So the expression, the asking of the question of inverse of A transpose is a valid question. How will we answer it? We will be computing inverse of A matrix, which we know very nicely, and then taking its transpose at the end. So now that we have determinant of A with me, I know A inverse is adjoint of A upon determinant of A. Let's compute adjoint of A. Adjoint of A is transpose of all the cofactors of A. C11, C12, C13, C21, C22, C23, C31, C32, C33. Let's compute C11. C11, it will be coming over here. Let's compute it from here. It will be -1, -8, so it is -9. Then C12, first row, second column. C12 is 0 plus 8, so it is 8, but it will be -8 because -1 to the power 1 plus 2 is -1 to the power 3, which is -1. Then C13 will be 0 minus 2, which is -2. C21 will be -2 minus 6, which is -10, so it will be -8. See, C21, it will be -2 minus 6, which is -8, so it will be just an 8 because -1 to the power 3 is -1. Then C22, second row, second column, it will be 1 plus 6, that is 7. Right, C22 you can see it is 1 plus 6, which is 7, and -1 to the power 4 is 1 only, so the sign is not going to change. Then C23, then it is 2 minus 4, which is -2, so it will just be 2. Then C31, third row, first column, it will be 3, 1, so it will be -8 plus 3, which is -5. 3, 2, third row, second column. Third row, second column, it will be 4 minus 0, which is 4, so it will be -4. And 3, 3, third row, third column, it will be -1, that is it, so it will be -1. So let's write it down, -9, -8, -2, 8, 7, 2, -5, -4, -1. Let's just check. C11 would be -1, -8, that is -9. Then C12, first row, second column, it will be 0 plus 8. So it will be just an 8 with a minus sign. Then C13, it will be 0 minus 2. So it will be -2. Then C21, it will be -2, -6, so it is -8 with a plus sign. So it will be minus of -8 basically, so 8 with a plus sign. C22 will be 1 plus 6, that is 7. Then C23 would be 2 minus 4, which is -2 with a minus sign, so it will be +2. Then C31 would be -8 plus 3. -8 plus 3 gives you -5. Then C32, third row, second column, it will be 4. So it will be -4, and 3 would be -1. So that is it. So here we have written it down, and therefore adjoint of A is very much there in our hands. What is adjoint of A? Adjoint of A is now -9, -8, -2, 8, 7, 2, -5, -4, -1. First row becomes first column, second row, second column, third row, third column. So inverse of A is adjoint of A upon determinant of A. Determinant of A was 1 only, so I am getting 1 upon 1, and this particular matrix, that is -9, 8, -5, -8, 7, -4, -2, 2, -1. This is A inverse, and inverse of A transpose is transpose of A inverse, so it will be -9, 8, -5, -8, 7, -4, -2, 2, -1. This happens to be your very value of inverse of A transpose. Is it clear? Moving ahead with the next question, we have, using properties of determinant, I need to show something, that triangle ABC is an isosceles triangle if this particular determinant's value is 0. Let's just consider this determinant and see, by solving it, applying transformations, what are we able to eventually get regarding the angles of ABC or stuff like that. So we have, this is a very nice determinant, it is 1 plus cos A, and then you have cos square A plus cos A, cos square A plus cos A. Then you have 1 plus cos B, cos square B plus cos B. Similarly, symmetrically 1 plus cos C, cos square C plus cos C. This is given to be 0. Clearly, what you would want to do, column 2 goes to column 2 minus column 1 and column 3 goes to column 3 minus column 1, so that you can get zeros in the next 2 columns and eventually can proceed in a simplified manner. So first column remains as it is, this is 1 plus cos A, this is cos square A plus cos A. 1 minus 1 gives you 0, 1 plus cos B minus 1 minus cos A, so cos B minus cos A. Then you have cos square B plus cos B minus cos square A minus cos A. So this will be cos square B minus cos square A, cos square B minus cos square A plus cos B minus cos A. Right, because you are getting cos square B plus cos B minus cos square A minus cos A. Next you have 1 minus 1, again 0. 1 plus cos C minus 1 minus cos A, so cos C minus cos A. Then you have cos square C plus cos C minus cos square A minus cos A, so cos square C minus cos square A. Cos square C minus cos square A plus cos C minus cos A. Now try to see this. This is equal to 0. You can write cos square B minus cos square A as what? Let's try to manipulate here itself. This is cos B plus cos A multiplied by cos B minus cos A. A square minus B square is A plus B into A minus B. Similarly, cos square C minus cos square A. Cos square C minus cos square A is cos C minus cos A into cos C plus cos A. Right? Now you can see cos B minus cos B minus cos A is coming out common. Cos C minus cos C minus cos A is coming out common. So let's take it out. I am having 1 plus cos A, cos square A plus cos A. Here you have 0 cos B minus cos A, and here again cos B minus cos A common. Inside you have cos B plus cos A plus 1. So let's write here cos B plus cos A plus 1. Similarly over here you have 0 cos C minus cos A, and again I am taking out cos C minus cos A common. Inside you are left with cos C plus cos A plus 1, and this is given to be equal to 0. You can clearly see cos B minus cos A is common in the second column, cos C minus cos A throughout is common in the third column. So I will take out cos B minus cos A from the second column and cos C minus cos A from the third column. I am left with cos B minus cos A multiplied by cos C minus cos A, and inside you have 1 plus cos A, cos square A plus A, cos square A plus cos A. Here you have 0, 1 cos B plus cos A plus 1, and here you have again 0, 1 cos C plus cos A plus 1. You can expand along the first row. what would you be getting is drastically interesting. Let me rub this previous step. You have already understood. Let me rub this as well. Okay. So here if you expand along the first row, so you can write expanding along the first row, what is it that you get? You get 0 is equal to cos B minus cos A, cos C minus cos A, and here you will have 1 into this minus 1 into this. That means cos C plus cos A plus 1 minus cos B minus cos A minus 1. Fine. So here you have plus cos A minus cos A plus 1 minus 1. You eventually are getting cos B minus cos A multiplied by cos C minus cos A multiplied by cos C minus cos B. Fine. This is equal to 0. Product of three things is 0. That means that this is 0 or this is 0 or this is 0. If this is 0, that means cos B equals cos A. Or this is 0 means cos C equals cos A. Or this is 0 means cos C equals cos B. Now ABC are angles in a triangle. So they are going to measure from 0 to 180. And in the very interval 0 to pi, cosine function is a 1, 1 function. So if cosine of B equals cosine of A, this implies B is equal to A, or C is equal to A, or C is equal to B. And in a triangle, if any two angles are equal, that means it is an isosceles triangle, which implies triangle ABC is isosceles. Is it clear? That's how you compute the very answer of the triangle being an isosceles triangle. Moving to the next question, using matrices, solve the following system of equations. In here if you try to see, this is the system. You know how to decode the system and convert it in a matrix format. From here we will be extracting the coefficient matrix. So A is 1 minus 1 2, 3 4 minus 5, 2 minus 1 3. Okay. Capital X will be given X, Y, Z value, it's a 3 cross 3 matrix, and B will be equal to 7 minus 5, 12. Is it clear? Therefore, system is AX equals B, and its solution is given by, X equals A inverse B. Is it true or not? This will be true only when A inverse will be existing. That is, will be true when the determinant of A will be non-zero. As determinant of A, when you find out, it comes out to be 4, which is not equal to 0. Therefore, solution is given by X equals A inverse B. I need to compute A inverse. A inverse is what? Adjoint of A upon determinant of A, that is adjoint of A upon 4. We just now computed adjoint of A. What is it equal to? It was equal to transpose of all the cofactors of A. Quickly, with the help of this A, try to compute the very transpose of all the cofactors of A and try to compute A inverse, and then try to compute X, and then you're going to get back and complete this particular question. Okay. So I hope you have computed this particular adjoint of A comes out to be equal to this particular matrices transpose, because this is the cofactor of the 1 1th element, 1 2th, 1 3th, cofactor of the 2 1th, 2 2th, 2 3th, cofactor of 3 1th, 3 2th and 3 3th element. And therefore adjoint of A comes out to be 7 minus 19 minus 11, 1 minus 1 minus 1 minus 3, 11, 7. And when you write over here 1 by 4, this actually becomes equal to adjoint of A upon determinant of A, which is A inverse. So you have got your very A inverse matrix, and so solution is A inverse B. This is 1 by 4, 7, 1, minus 3, minus 19, minus 1, 11, minus 11, minus 1, 7, and B is equal to 7, minus 5, 12. When you multiply these two matrices, you know this is 3 cross 3 and this is 3 cross 1. So you will be getting a 3 cross 1 matrix, and that would be coming out to be 2, 1, 3. If capital X is this, that means capital X was nothing but X, Y, Z. This is a 3 cross 1 matrix, 3 cross 1 matrix, both are equal, of the same order, that means their corresponding entries are same. So this implies your X is 2, Y is 1, and Z is 3. You have solved the system that if X is 2, Y is 1, and Z is 3, then all the three equations simultaneously will be satisfied. Okay, that's it from my side. Please revise all these questions nicely. Thank you.